Thank you all as you're trickling in today. Welcome to our tinyML talks. Today's speaker is Arindam Sanyal, talking about analog tinyML for health management using intelligent wearables. First, a couple of announcements and housekeeping. First of all, this series would not be possible without our tinyML strategic partners. Thank you for committing to take tinyML to the next level together. For those of you who are joining, perhaps for the first time, we have a vibrant community here in the tinyML. We have meetup groups with 12,000 plus members in 46 groups across 37 countries worldwide. And you can see the link here at Meetup to join. There is also a professional LinkedIn group with over 3,000 members and 10,000 followers that you can also join. In addition, all of these videos are on our tinyML YouTube channel. We have over 8,000 subscribers with 457 videos with 268,000 views. So really a great resource for all topics related to tinyML. And this video in particular will also be uploaded after the talk. So I just wanted to give an announcement for our next tinyML Trailblazer series, Success Stories with Christopher Rogers, CEO of SensiML Corporation. This will be live online December 7th. That's Wednesday, December 7th at 8 a.m. Pacific time. So please register now if you're interested in attending this talk. We also have another tinyML talk on Tuesday, November 29th. That's next Tuesday by Vitaly Kleban from Everynet on low-cost energy-aware sensor data acquisition at scale. The webcast start time for that is 8 a.m. Pacific time, so that's 30 minutes earlier than this one. And please, we're always soliciting interest for speakers, so please contact talks@tinyml.org if you're interested in presenting. So it's my great pleasure today to introduce Arindam Sanyal. He's currently an assistant professor at the School of Electrical, Computer, and Energy Engineering at Arizona State University. Prior to that, he was an analog design engineer at Silicon Laboratories and an assistant professor in SUNY. He has broad research experience in analog mixed signal design, biomedical sensor design, hardware security, and neuromorphic computing. And today he's going to talk about analog tinyML for health management using intelligent wearables.
Thank you, Suren. Hi, everybody. Thanks for attending. Today, I'm going to talk about some of the work that we have been doing in the space of analog tinyML for health management. Okay, so first this is the agenda for today's talk. First, I'll briefly talk about the overview of our work and the challenges. And then we'll go over some of the case studies and different tinyML architectures that we have been trying in our group. So we'll talk about some of our very simple analog artificial neural networks. Again, these are tinyML, like 3-layer analog artificial neural networks that we have prototyped. Then we'll talk about some of our works with reservoir computing, and then moving more broadly towards the goal of performing analog to information conversion on chip with these tinyML ICs. And then finally, we'll talk about a Fusion AI framework, and we'll talk about all of this for defined biomedical applications that we have been focusing on. So most of our work is due to its collaborative nature. We collaborate with other universities. We collaborate with SUNY and NC State, and for our medical partners, we work with Mayo Clinic here in Arizona and also with Emory University. And some of this work is funded by AFRL and SEMI and also NSF. So some of the motivation behind our work was to improve the disparity that we see in healthcare outcomes in US. So if we look at this chart on the top left, we'll see that if we look at the data from 2019, most of the uninsured are for ethnic or racial minorities and the elderly population. And at the same time, we see that the number of smart wearable users has been increasing. So so herein lies an opportunity to potentially improve this disparity in healthcare outcomes by having embedded AI in these smart wearables that can track patient health management at home without requiring clinical expertise, something very simple that the patients can do by themselves to monitor so that they know when they should, I mean, they get early indicators of when they should be seeking medical attention. And then this can potentially improve healthcare outcomes, particularly for cardiovascular diseases, which are often diagnosed late, mostly in minorities. The next other big motivation is to address. So we expect that with the next few years, we'll have a lot of these smart wearables. So all these smart wearables by 2030, they are expected to produce several petabytes of data per day. So that's a tremendous amount of data that needs to be transmitted from these wearables and then processed. So currently, most of these follow a cloud model. So that is, the data are collected from the wearables and then transmitted to a remote or cloud location where they are analyzed. So in all these cases of wearables, the major almost like 90% of the energy consumption comes during RF transmission. So having to transmit these petabytes of data, it creates two bottlenecks immediately. First, the communication network must be able to handle this data. And then at the device level, this essentially having to transmit all this data significantly increases the power consumption. So this RF transmission takes like 90% of the energy, while the actual sensing just takes 10%. Okay? So that again, so RF transmission reduces the time span that these wearables can operate without having to recharge. So our goal is that by adding AI inside these wearables, we can make these wearables intelligent, and then they can decide which data to transmit. So especially since our focus is on biomedical applications, especially for these biomedical applications, the wearables usually are tracking physiological data. So this physiological data by themselves, they are very sparse, and they are usually sampled at a much higher rate than the information content. So it does not make sense to transmit all, say, as an example for ECG signals, right? It does not make sense to transmit the entire ECG signals because most of that data is going to be sparse anyway. So it's from an energy perspective as well as from communication perspective, it's better if we can do local processing, analyze the ECG data locally, and then only transmit either the segments of ECG data that is medically relevant, maybe some segments that shows abnormality, or we can even, as we will show in our work, we can even only transmit prediction score for segments. So there are already this transmission bottleneck is well known. So there are several techniques that try to address this transmission bottleneck. Some of those try to improve the data acquisition scheme, or they try to improve the data converter. So they use either techniques like compressive sensing, or they use adaptive sampling data converters, which only sample whenever the input signal is changing very quickly. Or they also try to do source encoding, so compression techniques fall under this. But usually this kind of either compressive sensing or compression, or a better ADC, adaptive level sampling ADCs, they can offer only around 10x to 20x compression. So what we are trying is, by embedding an AI inside these wearable sensor, our goal is to compress the data that's sent out by ratios of 1,000 or 10,000, something like this. Of course, this also depends on how case to case. So if some patient really have a lot of significant events that triggers within a short span, we'll have to transmit those data. But usually most of these cases when we are recording ECG signals, we only expect abnormalities over a very short time. So that is by embedding the AI inside these sensors, we can compress this data significantly. So the challenge then shifts from the RF transmission to designing this AI. So the AI models that we design, they have to consume far lower energy than the transmission. Otherwise, there's no advantage in reducing transmission. So there are some well-known bottlenecks in trying to fit an ML model or MLAI model inside a wearable sensor, which already has limited resources. So there are some well-known challenges like von Neumann architecture. Basically, the computing and memory units are separate, and most of the energy is spent in communicating between these two units. So, and then there are well-known solutions for this also by having in-memory computing, which is very popular. So what we are proposing is to design these neural networks in completely using analog or mixed signal circuits, and then do the computations using charge domain. And then we can also store the neural network weights as values of capacitors. And then we'll show some of our works where we have prototyped just an analog, very simple neural network, and then we'll move on to our prototypes where we talk about reservoir computing and how we can use this particularly for physiological signals. So in this slide, this is basically the vision behind our work. So we envision that we'll design a fusion AI framework in which the sensor or the wearable device that the user will be wearing, that will itself have an embedded tinyML into the device, which will transmit either the prediction scores, or it can even transmit short segments of the physiological signal that show abnormalities. And then we'd just use this wearable device will transmit those segments or prediction score to a cell phone. And then at the same time, we'll also collect the patient's electronic medical records, or EMR, which would basically be their demographic information, some comorbidities, which we would have some drop-down list to select from. Like as an example, if you're looking at cardiovascular disease, this could be presence of hypertension, if there are any cardiac issues that the patient is diagnosed with. So any type of prior comorbidities, and then of course their demographics, age, race, gender, and so on. And then the ultimate goal is that we'll combine the scores from these two branches to provide a personalized prediction model for each patient. Now, this EMR model, this we can run inside the cell phone, and same, like we can also build a very simple meta classifier, again, usually like a 1-layer or 2-layer networks, which we can run on the phone. So we envision that if we can build this framework, this would be a very low cost and a simple technology for the patient to use. You would just need a wearable sensor and the cell phone, and then they can continuously monitor for different health conditions. The patient will be able to monitor themselves over long periods of time. So next, we'll present some of our works that we have been doing in collaboration with Emory and Mayo Clinic to develop these prototype test chips. So here, as the first case study, we'll present our work on developing an on-chip artificial neural network that would predict arterial fibrillation and sepsis. So we collected this data from patients admitted to Emory University Hospital over 5 years. So these patients are mostly, this data was collected from their EICU. So some of them had sepsis, some of them did not, but most of them had some disease or another. And I think a large part of them also had cardiovascular diseases. So the test chip at the top, you will see that we designed a very simple 3-layer ANN. So our goal was to design a single ANN that would predict both AFib and sepsis. And ultimately, we are using ECG as the physiological signals for prediction. And so we shared the first 2 layers of the ANN because we are looking for various abnormalities that are for AFib and sepsis. And then only in the last layer, we had the last output layers were different, where we trained them individually for AFib and sepsis. Now, to design the neural network, we used switched capacitor circuits. So all the multiply and add, they happened in charge domain. So we used once we trained the network, we used capacitors to basically encode the weights of the network. So value of the capacitances would change with the weights. And then it's basically like a very simple switched capacitor circuit to compute the math. So the advantages of switched capacitor circuit is that the computation is more linear than current-based computation, some examples of which are the more like popular SRAM-based in-memory compute. It's also easier to match capacitors well than transistors. So that's once we fabricate these test chips, matching is an issue because there would be variations from chip to chip, and even we would expect that these weights, their values would change because the weights are modeled as capacitors, so their values would change from the actual software weights we had. So it's easier to match capacitors than transistors. So this form of switched capacitor computations, they are usually like highly linear. So this slide shows those circuits in more detail. So the max happen in charge domain. Now to have an entire analog signal processing chain, so what we did was we also did the activation circuits using analog circuits. So if you look at say the common tanh or sigmoid, those sigmoid transfer functions, so they can be realized very easily using just like 5 transistor amplifier. So this any amplifier circuit, by naturally it has a sigmoid or tanh like shape. The only difference is that they are not exactly, they don't follow the exact mathematical tanh or sigmoid, but they roughly have that shape. So what we did was, in order to ensure that our test chips have same or accuracy as our software models, instead of using, during the training phase, instead of using ideal or mathematical activation functions, we took the SPICE characterized data from our amplifiers, and we incorporated that in our training model. So we incorporated this transfer curve as well as their derivative for the back propagation, and we built a MATLAB based model to train using actual circuit parameters. Now, these circuits, they have several non-idealities that we have to contend with. The first non-idealities are random variations that are introduced during fabrication. So that would change all the component values. But since we do switched capacitor computations, the results are basically in ratios of capacitors. So even if individual elements change, the final result doesn't change too much. Then the next source of non-ideality is these amplifiers itself. So during fabrication, there's random changes in threshold voltages of transistors, so that results in offset. So that would move the transfer curve, and it would ultimately affect decisions. So we have offset cancellation circuits that are built in. So basically they stored the offset, and even if there's change in threshold voltages, the offsets are stored in the capacitor, and they are cancelled at the output of the activation function, so that the transfer curves don't shift. In addition to this, there's also thermal noise, and it's well known that analog circuits are more susceptible, or analog computation in general, they have more susceptibility to thermal noise than digital computation. So we design these circuits, since these are mostly for biomedical applications with low bandwidth. We design these circuits to have low bandwidth and we burn enough power to ensure that the thermal noise is at an acceptable level. It doesn't degrade performance. So all of those are, during the analog design, we design these circuits very carefully to take care of offset, take care of matching and noise issues. So here we'll present some of our measurement results from test chip. So this confusion matrix, this is for AFib. For AFib classification, we classified as normal, AFib, or noisy. So you'll see that we misclassified 14 results. We misclassified them as normal, even though they were AFib. So we are also classifying if the signal is noisy, because that's important from the at-home monitoring perspective. Say if the sensor that the user is wearing, if it somehow, say the user has, because they will expect that the user won't be wearing that continuously, they will probably take it off and put it back on. So during, say, when the user puts it back on, if the connection is not good, so there we would have noise showing up in the ECG signal. So we are also trying to classify if there is noise, and we would send an alert to the user to check the sensor. So, I mean, overall, this test chip had a high accuracy, 98.8%, and very good specificity. So we also, to see the effect of noise, we took one test chip and we repeated the measurement, I think 1,000 times, and then plotted the histogram. We see that the standard deviation in accuracy as well as sensitivity is very less compared to 98% mean accuracy. The standard deviation is just 0.2%. And then we also measured its energy. So the energy per classification was only 12.9 nanojoules, which is better than existing works. Most of those are digital implementations of tinyML. So we also designed this test chip to look at sepsis onset. So we're trying to predict sepsis onset basically 4 hours before the actual sepsis. So here again, we had good accuracy. So you'll see that we plotted the accuracy and sensitivity of the test chip versus onset. So the closer we are to onset, the ECG carries more information, the ECG signal, that it basically has a more meaningful information. So closer are we to the actual onset, we can predict sepsis onset with higher accuracy. But usually we try to predict sepsis onset at least 3 to 4 hours, so that there is time to take medical action if we detect sepsis onset. Okay, so yeah, we can take questions.
Maybe well, I'll stop here to add, because there's some questions that have arisen. So Lewis Ross wanted to ask what sensor, so I think this is for the general application, or the what sensors are you using to collect the data, and how important is the accuracy of the sensors?
Yes.
Like, how does that impact that higher accuracy you have?
Yeah,
for your
that's a very good question. Actually, for this data set, as I said, we collected this from EICU in Emory Hospital. So I think they used the gold standard ECG data collection. So this ECG data is not collected using basically using our single lead ECG sensors. This was collected from the hospital. So I would expect this sensor data is very clean.
Okay, and do you have any knowledge of the accuracy of these sensors?
No, so these sensors are from the hospital, so they should be very accurate, gold standard. But to answer the question of how accurate the sensors need to be, so the short answer is right now we don't know, but as I will show at the end of this slide, so we have just started data collection at Mayo Clinic here with our sensors. So far we have just collected 2 patient data, but we are planning to collect more data from their patients going to the amyloid clinic. So then we'll know definitively how accurate our sensor is. But right now, these are all coming from these data are all coming from very clean and very high performance sensors.
Okay, and then Mike Stanley, one of our panelists, had a question, and I think I'll ask it for him. Are the weights hardwired into the circuits, or can they be updated at runtime? And if they are hardwired, how do you plan to maintain models over time?
Yes, this is a good question. For this chip, the weights are hardwired. So we cannot, for this chip, actually, we cannot change it. But in our later chips, we are planning to, move to basically a combination of SRAM and capacitive computation where we can change the weights. But for this chip, we cannot.
Okay, and Vadam had a question that's more technical. When you use a 5 transistor amplifier to get the sigmoid, the
Yes.
nonlinear region of the amp will vary a lot with PVT. How critical is that for the final results?
Yes. So it will vary a lot with PVT. So we do not expect a lot of change in temperature or voltage when we are using it to monitor, or at least for temperature when you are using it for at-home monitoring. The process and voltage might change. So what we do is, I haven't talked here, but now what we do is for the very last layer, we have a calibration step. That is, we adjust the threshold. So we have a small selected set of training data that we pick from this EICU, and for which we know what the accuracy is going to be. So what we do is for every chip at different, I'll show some results versus voltage later on. So for every chip, if we detect, basically there is a change in voltage. So what we do is we run those training data on this chip again. And then we use a nonlinear optimization to adjust the threshold. So just by adjusting the threshold of the output layer, we'll show that we get pretty good results as we change the voltage.
And one last final question
Yes.
before we move on. Marco asked, how many input channels are processed by your particular prototype?
Oh, yes. So if you're talking about ECG, so what we did was we used only a single lead ECG data for these results. So I think we use V6, channel 6 in the 12 lead standard 12 lead ECG. I think we picked channel 6 from that from those 12 leads.
Okay, great. Again, if you want to ask more questions, you can add it to the Q&A, but we'll continue on with the talk, and there's also time at the end to answer those questions.
Okay. So in the next part of the talk, we'll move to reservoir computing. So reservoir computing is it's a computing paradigm that projects the input signal nonlinearly to a high dimensional space. So it basically acts like a nonlinear kernel. So by projecting the input to an HD space, it makes it easy to separate the input classes using a linear layer. So as an example, so this data is collected from this is basically ECG data that we are using to predict stress versus non-stress. So at the input data, you can see that the two classes are very much mixed together, and then once we pass this through the RC, we can see that we can linearly separate these classes. So the advantages of reservoir, particularly for smart wearable devices, is that the reservoir does not need to be trained. That is, we can use any random time invariant random weights, so one-time random weights we can assign to the reservoir. This doesn't need training, or only the readout layer needs training. So it simplifies the ML circuit that we can use. Now, since the reservoir itself is nonlinear, So we can use nonlinear analog circuits to implement this reservoir layer. And since nonlinearity is what makes this separation easier, so from the power perspective, we can use very low power analog circuit, low power, low gain analog circuits to implement this nonlinearity, which ultimately improves energy efficiency. So here, as an example, we show an implementation of our reservoir circuit. So this reservoir layer, it has a nonlinear kernel, and then around which is basically embedded inside a negative feedback loop. Now, we built the nonlinearity using a very simple common source amplifier, and its nonlinearity shape looks like this. So, I mean, we can build other types of nonlinearity as well, sigmoid or tanh kind of nonlinearities as well. Again, very simply using a single stage common source, 1 or 2 transistor common source amplifiers. And again, for doing this summation, we need an op-amp, but since nonlinearity is allowed, this op-amp doesn't need high gain. It can slew. We can design all these analog circuits with very low power budget. So, and then this entire layer doesn't need training. So it means that whatever weights we put, so we used resistors and capacitors to implement weight. So even if those values shift after fabrication, and then these transistors threshold voltages shift after fabrication, it doesn't affect the performance of the reservoir circuit. So only thing we need to care about is this output layer, which we built using a logistic regression. So this one, for this particular chip, it was done off chip and digitally, but only the readout layer needs to be implemented carefully such that there's no shift or no variation in its weight or model performance. So we used this first test chip we prototyped in 65 nanometer. So what we did was we just built one neuron of the reservoir, and then we time multiplexed it. Basically, this one was running much faster than the sampling rate to realize. So using one physical neuron, we realized several virtual neurons. And then we use this to predict stress versus non-stress. So we use the data from there is a WeSAD dataset which has a collection of patient data for stress and non-stress, again predicting from ECG signals. So we achieved the highest accuracy so far at 27.5 nanojoule per classification. Okay, so the next step that we did was, instead of using a shallow logistic regression layer which is implemented digitally, we can build the reservoir, do not have an ADC inside the reservoir, that if we do not digitize the reservoir states. And instead of that, we can instead of digitizing the reservoir states, we can just take the analog values and send it to an analog artificial neural network similar to the one that we prototyped earlier. And we actually took these 2 test chips, an analog reservoir and the first test chip that I showed, the 3-layer artificial neural network, and we tried predicting sepsis with this. So in the lab, basically we had these 2 chips in separate PCBs and we measured. So the interesting thing that we see, key takeaway from this is that by using a complete analog AI model, we can for particular case of sepsis, we could reduce the transmission by a factor of 5400. Okay? So this is, again, we took ECG segments with 6,000 samples, and so just by sending the prediction score instead of digitizing the ECG data and sending all the ECG data out, we could reduce transmission by over 5,000 times. So we characterize several test chips. So these are 4 test chips that we characterize. So just to see the chip-to-chip variation, because the entire chip is in analog. So we see that they have very similar AUCs. I think the largest variation is between chip 3 to chip 1. So these are all like less than, these are around 0.2 to 0.3% variations in their AUCs. So here again, as I was saying before, so we had a calibration step, to a foreground calibration step, to ensure that we reduce the chip-to-chip variation. Basically, we have a small subset of the original training set. So for each chip, we run that small training subset through the chip again, and then we tune the threshold or offset in the output layer to maximize the accuracy on that training set. So by doing that calibration, we can reduce chip-to-chip variations. We can reduce chip-to-chip variations and increase accuracy. And in this plot here, we show that compared to a conventional way of transmitting digitizing basically all the ECG data and transmitting, where the transmitter consumes much, like more than 90% of the sensor energy, we can reduce the overall energy consumption by 160 times, and then reduce the RF transmission by 5,000 times. And in this slide, we show some comparison of our work with other work. So on the table on the top left here, we just show the comparison with several software models for sepsis prediction. So we see that these models predict sepsis at different times to onset. So the closer we are to onset, the higher the prediction accuracy is expected to be. So we see that compared to the other 4 hours, we have a higher accuracy, and we also have higher sensitivity, specificity. But the key takeaway is these last 3 columns. So we see that most of the software AI models that have tried to predict sepsis onset, so they use data from different sources. They measure several vitals. And then they also use the results from lab tests. So our goal is to build these devices where we can use this for at-home monitoring, where we'll definitely not have lab test results. So you see, for our work, we just use a single vital, just the ECG, and then no lab test. And then we still have similar or better accuracy, sensitivity, specificity as these models, which use a lot of these lab tests, a lot of these vitals. And then just for the hardware, we tried to compare it with different AI accelerators. So these are mostly macros which compute Mac operations, just the multiply and add, rather than building a complete tinyML kind of circuit. And so in summary, we see that we have like a comparable energy efficiency as these macros, even though we build the entire model. So we also have the communication energy between the models and energy of activation functions. Okay, so the last section of the talk is our fusion model. Okay, so far we have talked about how we can use the patient's ECG to make these predictions on stress, cardiovascular disease, sepsis onset. So we hypothesize that we can improve the accuracy of our models further if we combine this with the patient's electronic medical records, basically their demographics and comorbidities. So what this is, again, what we did is, so this is the first work where we are just predicting sepsis using our ANN. So there we also had, so this was from the Emory University Hospital dataset. So we also had the patient's EMR collected. So we combined the patient's EMR with the ECG. So you can see this plot. So we see that just the orange is the on-chip prediction. So this is the prediction versus time to onset. So the prediction accuracy increases as we get closer to the actual onset. But then when we combine this with the patient EMR, we see that we improve performance by almost like 5 to 6% across all these different times to onset. And so fusion, like we see that fusion provides meaningful and significant improvement in accuracy, and this can lead to a personalized prediction framework for each patient. And then, here we also show these results, like variations work across chip and variation with supply voltage. So we see that for the on-chip model, actually, like as we change the supply voltage, even with calibration, the accuracy drops. Most of the accuracy drop is just due to thermal noise increase. So compared to 1.2 volt, if we go down to 0.8, the accuracy drops by almost 6%. But here again, we see interestingly that once we use fusion, because the EMR is independent of the supply voltage, so the accuracy still drops at low supply voltages, but most of that is due to drop in on chip. So once we have the fusion model, the accuracy drop is not so much. It's more like less than 4% compared to 6%. So fusion can also improve performance even though the chip's prediction performance drops. And then this is just chip-to-chip variation results. So the ECG sepsis prediction based on ECG, that performance varies like from 85 to 87. So there is roughly like 2% variation from the worst to the best chip. And then we applied this similar fusion technique to our reservoir computing chips also. So here we worked on a different data set of trying to just predict cardiovascular disease or not. So here again, we see that with different chips, we have like around 77 to 78% accuracy. And then once we combine this with a fusion model, the accuracy is improved by 9 to 10%. So for different data set, I think this is another data set where, so this data set, I think this is still the same sepsis data set. So what we did was, this is that here the hardware was the combination of reservoir computing and the analog artificial neural network. And then we performed fusion by adding the patient's EMR. So here again, we see that, just the on-chip for different chips, there's chip-to-chip variation around 1 to 2% throughout the different times to onset. And then once we combine this with fusion, we see on an average, it increases by 12 to 14% throughout. Some cases it's less. So the closer we are to onset, because EMR, just the EMR by itself, it's time invariant. So closer we are to onset, so addition of the EMR does not increase the model performance as much if considered, say, if we are very far away from onset, where the EMR has addition of EMR can improve the performance. But in general, fusion improves the performance always compared to the on-chip, compared to just the prediction from ECG itself. So, and then this is the latest step where we are at currently. So this was on one of our volunteers at Mayo. So this is not like the picture of our test with actual patients, but so most of this data, most of these devices are to collect the data and display on a laptop, but this is our test chip. So we are going to the Mayo Clinic Amyloid Center regularly to collect patient data. So we are trying to collect patient data and then validate our chip's performance as well as the fusion model's performance on that. So so far, all the measurement results I showed, they were from retrospective data collected from hospitals which are already cleaned. So here we'll know how much the sensor's performance can affect the model's performance, and how and say if there's noise, and so some of these data that we are collecting, they are when the patient moves during data collection, so there's noise and artifacts. So we are also going to see how our analog AI models perform when there's noise and artifacts in the collected sensor signal. I think that's the end of my talk. Thanks for attending, and I'll be happy to take questions.
Okay. Thank you, Arindam, for the talk. We have some time for questions, so you can feel free to ask your questions in the Q&A still. So I will start off with a question here from Marco. How would you explain the improvement in robustness against voltage and process thanks to fusion?
Oh, yes. So just the chip data, right? So it is sensitive to variations in voltage. So as we saw that as we reduce the voltage, the accuracy drops. But the EMR also, so part of the fusion model, part of we have contributions from both the sensor data as well as the patient's electronic medical records. So the electronic medical records, maybe I can, oh, sorry, I can go back to this. Okay, so the electronic medical records, that performance is invariant, I mean, independent of the supply voltage. So even though the performance from the chip drops, since the EMR performance is still unchanged, so the overall performance is not as bad as just from the chip itself. It's just due to the combination of the two different modalities of prediction.
Okay, I'll ask one more technical
Yes.
question, and then I'll get to some broader questions here in the Q&A. So for this reservoir computing, the random assumption is kind of interesting. Is there some critical assumption, like, not all random is the same? I assume things like thermal noise or things that are like very normally distributed are okay, but is like systematic bias or drift? Like, can you comment more
Yes,
on the randomness?
yeah. So we want to generate. These weights to have a random distribution. But if, as you said, if there is bias, so bias here in the circuit, it would show up as offset in the amplifiers. Yeah, for this case, it would mostly be offset in the amplifiers and offset in the ADC. So bias would skew the decision towards one class. So bias is something that we don't want, and we calibrate. So for the ADCs, we calibrate the offset. For this also, basically here we had an ADC in the loop, so we could do the offset cancellation at the output of the ADC. But yeah, we do not want bias in this in the weights, or in the basically, yeah, here it's just weight. So we do not want bias in this network, but we still want. So again, when you talk about randomness, we want that randomness to be time invariant, not exactly like thermal noise, because we do not want the chip's characteristic to change with time. So this randomness would mostly come from errors introduced during fabrication. So we use very small components and assume that, I mean, during fabrication, their values would be normally distributed. So whatever we depend on static mismatch to get to this randomness, but we do not want randomness coming from thermal noise, or we do not want bias coming from offset.
So you have to design the circuits to account for some type, still things like thermal noise and that,
Yes.
but you,
Yeah.
you may be less worried about mismatch and
Yes, we are less worried about mismatch and nonlinearity, but thermal noise and offset still have to be cancelled.
okay. So now some more broader questions in the Q&A. Maybe let me start with one of them was concerning just intelligent wearables for analog tinyML devices. What would be like, you think like a down, like what would be the final cost of these wearables, and like would that cost be a hurdle for these uninsured minorities, these
I don't, yeah,
vulnerable
sorry,
groups?
yeah, sorry. Yeah, I'll let you finish. Sorry.
Oh no, no, sorry, I was just
Okay.
completing. Like how would it affect the most vulnerable populations?
Yeah, so I would expect that these are all built. So these circuits are all CMOS based and it would integrate with the existing sensors. So I would expect that if bulk produced, these CMOS circuits should, I mean, even a very complicated uh, timing circuits from companies like Silicon Lab that sells on market for $10. So uh, if this can be bulk produced, it should be overall, I think the sensor and chips should be less than $100. But yeah, um, it depends on bulk producing or if this can be bulk produced.
Okay. And the second question here is maybe more related to education or training.
Yes.
Kind of if you're getting started and you're taking these input data from smartwatches and applying it for different healthcare diseases or anomalies, do you have like kind of a maybe like your kind of like recipe or like do you have to do this design process for every new type of problem you need, or is there some like transferable steps or processing with this reservoir computing plus
Mhm.
fusion methods?
Yes. So good question. So for the reservoir computing itself, so we have tried this on different data sets. So I mean, the reservoir itself does not need training. So uh, only thing that you need to retrain is the output layer. So that would need retraining from application to application. And we have a pretty good now MATLAB interface based model setup where we can do this training quickly. Now, the EMR, again, if it's just like we have been collecting patient demographics and their comorbidities. So that, so the EMR model as such does not change, but it might need retraining from application to application because the model would change. Um, so there is not a big change when we go to a different application. So the major change would be just the retraining the output layer. So the structure won't change. So the weight should change. So we'll have to, if we go with this capacitive type of neural networks, we'd have to redesign. And then we are planning to move to an hybrid SRAM plus capacitor where we don't have to redesign the network. We can just program the weights from outside. So going from application to application, it wouldn't take a lot of change.
Okay, two more questions coming in. So I think these are kind of related. Lewis wanted to ask more about the actual sensing data and sensors used, pressure, inertial combination, what's actually doing the sensing. And further, another person asked, like, is this a 3 electrode setup for ECG sensing? And how would you use these wired electrodes integrated into a wearable?
Yes, that is a good question. So most for this measurement data that we have shown so far, so they were all, they said they were collected from the hospital with 12 lead ECG. So from there, we picked a single lead. Now, what we are doing right now is this. So this new data that you are collecting at Mayo, so they are with 3 electrodes. So this, I mean, here we have shown on the wrist. We don't need to do it on the wrist. Now, ultimately, what we envision is a device kind of like this, where you put a small device with these 3 electrodes placed very together in the collarbone region. There we have found that, I mean, the motion artifacts is much less than the wrists. So we can have a single device with the 3 electrodes and then the chip also included. So overall, we can encapsulate that and have a small device placed near the collarbone.
And a follow-up question from that attendee was, how will recording artifacts from this setup affect the computing?
Yes, so we are, I mean, so for all the prior data, again, I mean, they were collected in the EICU. So the data that we got from them, it was already clean. There were no artifacts. So this data that we are collecting, this has artifacts, but so far we have only collected 2 patients' data. So we need to collect more data to look at the effect of artifacts on our chips. But most likely we would need to do some bandpass filtering because some of the artifacts have a big, they have a much larger amplitude. So you probably have to do some bandpass filtering, but we don't know that answer yet.
Okay. Great. Well, thank you so much, Arindam. So again, I'd like to thank the tinyML strategic partners for help sponsoring these talks, especially our executive strategic partners, ARM AI, which is sponsoring these virtual tech talks that provide the latest in AI trends, technologies, and best practices from ARM and ecosystem partners. Edge Impulse, the leading development platform for Edge ML. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Sentient, making Edge AI a reality. We'd also like to thank our Platinum strategic partners, DeepLight, the fastest video analytics solutions on ARM CPUs and an AI Trailblazers award winner. Clicka Global IoT Solutions. Renesas, in enabling the next generation of AI-powered solutions that will revolutionize every industry sector. Sony Semiconductor Solutions Corporation. And also our gold strategic partners, including Analog Devices, where what if becomes what is. PhotoHub, making over-the-air firmware and ML models updates simple and accessible. Microsoft. NXP, together we accelerate the breakthroughs that advance our world. SenseML Analytics Toolkit Suite to make or break your next smart IoT product. ST Microelectronics provides extensive solutions to make tiny machine learning easy. Synaptics, engineering exceptional experiences. And lastly, our silver strategic partners listed here. So just as a reminder, next Tuesday after the holiday, November 29th, is a talk by Vitaly Kliban from Everynet on low-cost energy-aware sensor data acquisition at scale, and it will be at 8 a.m. Pacific time. Please, again, contact talks@tinyml.org if you're interested in presenting. And with that, we want to thank you. We hope everyone has a good holiday wherever you are in the world. And we hope you will join us again for future tinyML talks. So thank you.